Good morning everyone, and welcome back to our channel. We continue with our tutorial on CNC turning machine programming. So, we have seen in these videos that we can move in G0, G1 in, linear interpolation by entering two coordinates and creating an inclined line according to the arrival point X and Z, or according to the angle. We know how to make chamfers, and we know how to make radii. We have recently discovered that we can correct our profile to make it exactly uniform with the drawing by adjusting the tool radius correction. I tell you that outside of threading. If you have followed our tutorial up to this point, you are able to execute the programming of 100% of the parts that can be obtained for two-axis turning operations. Let's do a small example. This is a small example of a piece that I came up with. We have never talked about grooves, we have never talked about drilling, but we have talked about programming in X and Z. Nothing else is needed regarding how to manage ourselves. Regarding how to manage ourselves, let's assume a metal piece, diameter 80, to be brought to this drawing with a 1 mm excess material on the face. So we will need to face it, hollow it out, drill, and make the groove. Okay, so the order of operations will then need to be optimized based on the users, the turret, the operations we need to perform, and the type of finish. Let's not worry about that. Let's focus on making a small program. Unfortunately, I only have a whiteboard available, so we will go step by step. So, let's take our program. At the beginning, we need to give our percentage. Let's call it 100. I will refrain from writing comments because otherwise the video would become particularly long and boring, so I will explain. A few things. First, we need to set G92 S2000 to limit the revolutions when using a simulator. Here we will also define our raw material to allow the graphics to work for us, becoming our eyes, and we will see it later in the simulator before making adjustments and avoiding unpleasant surprises. After that, we insert G95, so we tell our lathe that we will work in millimeters per revolution. Let's rotate our spindle. So M4 S200. G96, so it rotates in a sense. Sorry. Then it's not always necessary because small lathes don't have it. Lathes with gear changes will require M41 and M42. Let's set it. It won't hurt. And let's rewrite M4 S200 G96. Perform the next turning operations at 200 meters per minute. So adjust the revolutions based on these 200 meters that must occur at the tip of our tool. So accelerate as I move towards the center with the limit set to G92. I call a turret TO1 and here I will write a nice comment about what tool it is and what operation I'm going to perform. I am going to do the facing. That is, I want to remove all this excess metal in one go. Let's not worry about the correctness of the operations, but about the movements. Okay, now in rapid G00 I will go to where the piece is. We said it is a raw material with a diameter of 80, so I will go to X85, giving it a 5mm clearance before going to hit Z0. Okay, very educational. If I were on a machine, what would I have done first? First, a nice X200, Z300, then first Z0 and then X85. I have brought myself here, perfect. G1, let's do this piece. G1, X0, actually, let's say I have a tool radius of 0.8, so minus 1.6, F0.3. 0.3. All right. This is definitely to get to this point, to correct the tool radius. Do not leave. Small bevel, the tip. We have faced our piece. In fact, I always recommend reaching X10 and slowing down a bit, because if we have the tool high-low, we could stress the tool tip. I provide you with this information, even though programming is more about tooling, but it's good to know. So normally I program G1 X10 F03 1.6 F0.1 to avoid stressing the tool tip too much. Well, I have already faced it, so we have already eliminated this part. G0, G0, X300, Z300. If I had put an M8 and an M9 here, I would have opened the water during the facing and removed the coolant. Okay, in some materials it is used, while in others it is not. This also goes beyond pure programming, depending on what you have in the machine. Here, it is not specified whether we are using C40 or C42 chrome of 0.4, but now we are focusing, I repeat, on the tool path. Now, we know how to make the profile from point 0 and follow it all the way. This is because our concern is to move in space. Now with the same tool, if I want, I can go and remove all that excess material. So, instead of moving away completely, G0, Z3, I leave the water on. And then, still in G0, so I won't repeat it, X70, let's say we have a nice sturdy insert, and we can easily remove 10mm at a time. So here, G1, Z 19.9, okay, 19. Z 19.9, I have roughened the first part. Now there are two ways to proceed, or I save. So every time, excuse me a second, I never remember if U refers to X or V. So here I can use U10. Do you remember? Incremental. In X, I raise by 10 mina, so I go back to 80. And the possible inclination of the insert that is cutting and is left is straighten to avoid unpleasant lines during the finishing phase, G0 or G00 Z3. So what I did was finish the chamfering. At Z3, I moved to X70 quickly, went to 19.9, U10, returned to X80, and then G0, Z3, I went back to Z3. Always check if you need to write U10 or U5, because some machines are radial, okay, regarding just the U, perfect, Z3, X60. So I will write X60.5 because I leave a bit of excess material, and then I repeat clearly what I wrote above. So G1 Z19.9 U10. So, I positioned myself here, made my pass, raised, to straighten the tool's clearance angle, and at this point I can move away. Quickly, GO0X300Z300. All this excess material is no longer there, and I did it with point-to-point programming. It's quite a mess. Soon I will explain that it's not necessary to do all this, because if the distance, instead of being 20 mm, were a rough diameter of 200, reaching 60 of these lines, we need to write 1000. But CAD/CAM, when they output their programs, they still output them like this, because it has its own logic. Fortunately, fixed cycles exist. In fact, at the end of this brief lesson, which mainly serves to help you understand that you have already learned to program, let's talk a little about fixed cycles and introduce the concept. Well, what do we do? Well, we change the tool to finish, so T02, T02. If necessary, the cutting speed is also changed. It is always better to include the cutting data when calling the tool. Why? Because if you interrupt the cycle halfway, you can start from the tool recall and it will already read the cutting data. G95 is not necessary, but M4, S200, G96, yes, M4, S200, G96, yes, M4F. 300 because here we will really take away very little. G96. Here I move over and do the finishing. I will position myself. So we have chamfers of 145, a cylindrical turning, a radius, and a groove that we will ignore for now, because to finish we will use a DNMG insert, a VNMG, at 35 degrees and 55 degrees. Obviously, I can't do the groove, so I will go quickly. AGO03. This is 1 for 59, but we are a bit lower, at X56. At this point, what am I going to insert? I will insert my tool radius compensation, G42, because I am moving the profile clockwise. G42 will work well if in the tool table, and we will see this later when we do the first program, Simulator. We will have inserted the correct tool radius and a small drawing. I would say the correct orientation of the tool. We have mounted an external tool, a boring tool, an external pull, or a boring tool in pull every 1, 2, 3, 4. Each machine has its own way of having this information. There are machines that require this information at the end of the tool change compilation, and many other machines, fortunately the more modern ones, ask for it graphically in the tool table. We are already starting to get into some very interesting programming concepts, so follow me closely. I hope to convey all of them to you. If you listen the first time and don't understand, try watching the video again. You will see that the second or third time, especially when we take the simulator in hand, these concepts will come to mind and will definitely be much clearer. Now notice that I have arrived at G00 and only after set G42, Z3, X56, then G1, Z0, F0.2. The first movement, Z3. Z0 must always be at least twice the radius of the tool. Otherwise, on some machines, G42 can be a bit troublesome. At this point, let's do our chamfer. Let's make a cool chamfer. So, a chamfer, according to the standards of the automotive industry, expanded upon. Here, and here, and in various other aspects here, are 0.15 R, 0.15 chamfer 1 for 45, This is a remarkably cool chamfer, as the Germans want it to be designed in such a way that we don't use C. Instead, we use both A and R parameters effectively. How do we create such an impressively remarkable chamfer? With our direct programming. So you can choose either option, comma, followed by an A, depending on which CNC machine you have access to, or also equal if your system supports cymes at angle of precisely 90 degrees, henceforth proceed upwards. Directionally speaking, comma, then follow up with R set at 0 value. A 135 Z1. This is roughly, approximately a minus Z1 X60. R0, I am truly sorry, but I really need to take up significantly more space. As we previously discussed, and this is important because it affects our overall plan, and this is crucial for our overall strategy, so we said, comma, a 135 by 60, which is quite specific, as it directly impacts our planning, Z-1, comma, R 0.15. What does it mean? I go to X 56, Z0. I'm here, then I tell it to go up. At 90 degrees, I give it some information, you stop at Z minus 1 X 60, and you reach 135 degrees, which is 45, and in both cases, it finishes the trajectory with a 0.15. Here, the machine can go here, making the infamous cool chamfer G1, which is not necessary to repeat, Z minus 20 X 80, comma, R3 is minus 24, and we have arrived here. Look, we have reached the end of the chamfer. G1, Z20, X80, R3. So it finishes the trajectory with a radius of 3 and goes to Z24. Be careful. If I had written Z22, I would have obtained a radius and error. This Z must be at least 3 mm.100th. It's superior in movement, otherwise it can't give me the radius. From 3G00X200Z, 300 M9 M59. Well, now I will continue programming M9 to stop the water that I turned on here, and M5 to stop the M4, that is the spindle. You see that with our programming made only of X and Z, so without macros, without complicated things, and there's nothing complicated, but without important names, like macro instructions or fixed cycles, we have profiled our piece. Okay, we have profiled the piece and it's a mess, but now we have a hole to make. And every time I have to lose at least once on the board. A hole in a groove is a point to point. I will completely ignore this chamfer. So, to drill, just take a bit, zero it here in Z, and set it to 0 relative to X. So when I want to drill with a bit, I always drill at X0, unless I use an insert bit. The insert bits are 180 degree bits. If we look at them like this, they have an insert here, an insert here, and then an insert here that we will see, and an insert here that we won't see, interchangeable. If I have a 32-bit, I zero it at this point like a reamer and drill at X 32. If I have a 40-bit, I drill at X 40 with the small detail that they usually have 0.8 tenths depending on the diameter of the bit. Even 1 and 2, a type of off-center. So a 32-bit can drill at 32.8. Insert bits are very interesting because after drilling, they can retract and work like reamers. Okay, now we stick to the classic, to not complicate life too much. But we don't complicate our lives with insert bits. On the contrary, we make it much easier. Trust me. But let's stick to the classic and drill with a 10 spiral bit. Simply. So, when drilling. Nowadays the bits, unless using special materials or very long holes, a hole with a diameter of 10. Diameter approximately 30 millimeters. Therefore I call my tool holder T3 T0303. At first I set my spindle to M3S, initially at a speed setting, subsequently adjusting it further precisely. Under G97 protocol with an exact speed of S800. Please ensure you are vigilant and watchful for these specific types of drills when utilizing M3. This step is crucially important. NVIDIA brand-specific drill bits, as well as integral, helical drill bits function centrally within operations like classic G97, drilling at a consistent fixed RPM rate, such as exactly around 800 revolutions per minute, RPM. The tip gets inserted carefully into position. However, since they're programmed based upon their respective diameters, one can operate them either maintaining constant RPMs, but also potentially opting instead towards choosing constant cutting speeds, both options providing great operational flexibility advantages. X0. M8 water is always very important. Essentially, I position myself right here in front, and then I proceed with G1, Z30, F012, G0, Z5, and I come out. I successfully made it brief, very high performance. And efficient drill, I enter in one solid body and exit. In reality, we have specific macros that allow us to effectively break the chip, so we set the feed rate right away, so we absolutely don't have to worry about it anymore. F0.15, yes. Indeed, the feed can also be set in a single block, not G1. We will carry it forward until we eventually recall it. Then G1, Z5. Let's do 10. Otherwise we'll do a lot of unnecessary steps. 10, V1. G1, Z20, V1, G1, Z30, G0, Z5, every 10 minutes. To the depth of the material, we have broken the chip. And then continue to ensure precision and accuracy in the process and maintain the integrity of the operation. We returned in incremental mode by 1 millimeter on the Z-axis and then moved forward to Z20, then incremental by 1 millimeter. Of course, we can do it millimeter by millimeter. We could even exit the piece, that is, instead of V1. Let's do it here instead of V1. We could put G0, Z5, Z19 here and then start. Okay, I mean to really clear the chip, because at the tips, chip sometimes doesn't break, it gets in the way, and when the chip doesn't break, what breaks is the tip. Which macros help us? Okay, I repeat. With the current tips, especially on steels, there isn't this great necessity. But I am on aluminum maybe because it doesn't clear. It can be useful on the FE that makes very long chips. It can be useful to have this discussion about chip breaking. The macros help us, but with our simple and straightforward programming, we can also do this. Now we have drilled the piece. Let's leave the chamfer aside. Otherwise this video will go on forever. But we have a groove. We can make a groove. I haven't taught you anything about grooves, and of course we can make a groove. Let's take our groove tool. We know that our tool has a thickness of 4 and we zero it. Well, we only need to move our virtual point according to X and Z, so our tool point. So what do? We should position ourselves in the middle of the groove, truncate it, and then finish it because this groove is made like this. I didn't draw it for you because I didn't have space before, and these two small chamfers can be, in fact, let's say one side is a radius and the other side is a chamfer. It's a tricky groove that really wants to annoy us. Well, we can certainly make this groove point by point very simply. What do? Let's not worry, as always, about many things like chips. The chamfer is 1, the radius is 1, the groove is 5 wide and 5 millimeters deep, which means it goes from a diameter of 60 down to a diameter of 50. Let's call the cutter blah blah blah, put in all the cutting data, generate it, M4, and in G0 we move to X61. I wrote Z5, but that's not right. Let's go to Z, at least 14.5. So we position ourselves here, more or less, then we tell it. G1. Excuse me. 81. 60. Yes, no, written correctly. X. We said that a depth of 5 means that diametrically it is 10 millimeters. We say X 50.3, F 0.08. Be careful. At 50, we can go there in one go. That is, implanted. Or we can do the same thing. We saw, for the tip. We go to X57. We detach by a tenth. X58. We detach by a tenth. And so on until we reach 50.3. This is to facilitate chip breakage, which is notoriously a breakage of balls in grooves. After that, we move, return in G02, X61, and we make this profile, taking into account the thickness of the groove. So Z minus, here is 15, let's say 16. We do not take into account the virtual radius of the tool in this case. We make exactly the profile. Then G1, X60, comma A in this direction. So in this direction, minus 45. This is minus 15. And here I am at minus 16. How much do I move to make a groove 5 wide? With a 4 tool already roughing the groove? Because we have already discussed this with the first implant. I am here at 45 Z15. I go to the bottom. So G1X50. Obviously, I will just need to widen by 1 millimeter. So Z14 and return to X60 are 114. And return to X. We should tell him at least he's 12.5 to allow him to round off, and we would have made this small discussion. Okay? Obviously, if we don't do more than well, the zeros will leave small lines here. So, when you do the actual programming, either you come away or you come inclined, but everything with a point. You understand that making programs this way is quite complicated. I forgot all this, but it is not complicated. It is laborious. However, this does not allow me to perform a specific operation that, with point 2, cannot be done. Namely, threading and tapping, which are two twin operations. So, for tapping, there is a fixed cycle that we will see later. And for threading, there is both a fixed cycle and let's call it its dedicated interpolation. That is, G1 and G00 are linear interpolations, fast and slow. G2 and G3 are circular interpolations in one direction and the other. G33 does not exist as a term, but we invent it. The threading interpolation. So if I wanted to make a thread here, okay, M60 for 2, what should I do? I have to call the tool that does the threading, give the usual cutting data, and then tell it G0Z3X, well said 60 for 3, so let's say X 59.5 G33Z from here, almost 10 millimeters, so Z let's make at least 14. 59.5 G. From 4 to 4 is 10 meters, Z minus 14. Z minus 14. F3, where G33 tells the machine, look, I am making a thread. Go to F3. You will ask me what the difference is between a G1 at F3 and a G33 at F3, which is that when I detach, because a thread is never made in one go, so pardon, when I finish G33, first of all it returns here. So at this point I will tell it G0, X 59, X 59, G33, ZD14, F3. That is, what does the machine do? It resumes the thread. I tell you the truth, I have a doubt about returning to Z3, so in case, Z3, X. 59 because I have a doubt, because one cannot think of making all the threads. Putting in, we have an M3 thread. For example, the thread is too deep. We want to make passes at a depth of 0.2 micron, so we need to use G33 10 times. This is why G33, every time you repeat it, resumes the thread. So with G33, at this point, you are able to perform external threading with a threading tool or internal threading. Okay, with a threading tool, but not with a tap. This is why at this point, the macro, the fixed threading cycle, comes to our aid. So what are these macros? What are these fixed cycles? Fixed cycles. And this is where it gets interesting today, forgive me. But the video is quite long. Fixed cycles are those that allow us to avoid writing 20 or 30 blocks. I won't go into much detail about G33 because you will see that in practice it is almost useless, or at least it has always been for me. Then something is useless until you need it. So I was saying fixed cycles are those cycles identified by a G, which in the case of external roughing can be G71, allowing you to summarize in a maximum of 2 lines what you would be forced to do in 20, 30 or 40 lines. Okay? So the fixed roughing cycle allows you to determine the dimensions of the blank and rough out all this area, either internal or radial, with just 2 lines. The fixed cycle is always a fixed roughing cycle. Some things change, some details, for example, the G that distinguishes it. Then there is the fixed groove cycle, the fixed cycle for front or radial grooves. The fixed cycle for grooves is especially useful when the grooves are large, because you will see, unlike conversational programming, the fixed cycle. does it this way, it does not allow you to add chamfers, arches and grooves. What about that? However, if you have a front or wide groove of 30mm to make with a tool of size 4, 5 or 6, a fixed cycle will definitely be useful. Once you have determined the width, depth and position of the groove, it will clear it for you, breaking the chips with a fixed cycle for threading, tapping and drilling. Also, these fixed cycles for threading, once you provide the length, pitch, diameters and depth of cut, it will handle the back and forth for you. Tapping, tapping. It cannot be programmed. It can only be done with a fixed cycle because you need to enter at a certain feed rate, gradually slow down the spindle speed until it completely stops, reverse the direction of rotation gently, and exit. Therefore, tapping is not programmable in standard ISO, but requires a fixed cycle. Drilling, as I mentioned earlier, is now done with modern tools, but it is a fixed cycle that allows you to enter, exit, and detach. So, if you want to stop for just a second to break the chips or exit the hole, you have a hole with a drill 7 times the diameter. You will definitely need to exit the hole sooner or later to evacuate the chips. The fixed cycle does this for you. Okay, so in the next videos we will look at all these fixed cycles. Obviously I skipped it because it is really basic. There is also a fixed finishing cycle, meaning when I have roughened, I can also finish with a fixed cycle without having to repeat the profile multiple times. If I forgot any fixed cycle, don't worry. If someone is already experienced, don't jump on the chair if you forgot this fixed cycle, because we will see a bit of everything. Now, here is a quick reference guide. Roughing, long axial roughing, drilling with chip breaker, cycle for front grooves, radial grooves, threading. I would say that fortunately these cycles are better oriented, a bit of everything. So now remember that our programs will become a sequence of X and Z, alternating between fixed cycles and X and Z. The fixed roughing cycle, for example, is identified by a G that identifies the cycle. I won't write down which G it is now, because it changes if you change CNC. After that, we will need to position our machine at a point almost coinciding with the extreme point of our blank and give our machine what? The depth of our cuts, the excess material in X, and Z, that is, how much excess material. I will leave for the tool to finish mine, and let's see the so-called disengagement distance. That is, every time I rough, how much I need to disengage before returning. Given these simple codes, what does the machine do? It will read the finishing profile and adjust all those passes that we have set. I hope not to bore you too much, but I also don't want to rush. So I prefer to explain things gradually. Today you understood that with point-to-point programming and direct programming, you are capable of making any required profile in turning. The only thing is you need to do many steps, many blocks, and you have to write a lot of code to do it. However, by now, you are able to create a profile, make grooves, and the grooves we saw on the diameter can also be made head-on with the same principle. You can make a hole. So if you can make a profile externally, you can also do it internally with G33, one pass at a time. You can also make threads inside and outside, as long as the tools are not male. What more do you want from life? You are missing only the ability to mask, and I would say that already, with everything I have shown you so far, you can do most of the work. Well, I hope I haven't bored you too much, but if you like the surely not, next time we will see the internal, external, longitudinal, and parasitic roughing macro, and of course the finishing macro, as the two go together. We will start practicing with the simulator. Regarding the simulator, there is already a sort of course on my channel, but it is mainly dedicated to the FANUC, where in part 3 and part 4 I provide the information, so I won't repeat it, about using the FANUC simulator, which you can download from the Ecco website. It is called WinC and is the FANUC 31 ITD simulator. Once downloaded, install it. The only precautions are to choose Tournament 4 and 60 when prompted, and when you finish, go to the program called WinConfig and choose Interpreter B from the various menus, otherwise it won't read the macros. But also, on my channel, you will find the tutorial for installing it. Once installed, you have 30 days to practice. After these 30 days, it becomes a demo, so the fun ends. You can download the software on your little sister's or brother's PC, depending on how old you are, or your child's, if you are old like me, and use it for another 30 days. So don't rush to download it. Follow some tutorials first, and when you feel ready, download it, and you will see that with it you will practice very, very well. Well, thank you. I have bored you enough. I greet you, and I look forward to the next tutorial. Thank you all, and have a good day.